this day colloquium, I have the pleasure to introduce Professor Vangelis Harmandaris. Vangelis got his bachelor degree from the University of Patras in chemical engineering in 1996. He then went on to do a PhD at the same university, again in chemical engineering, graduating in 2001. He was postdoc at the Max Planck Institute for Polymer Research in Mainz from 2005 to 2009. And then he was elected assistant professor at the University of Crete, at the Department of Applied Mathematics. It is particularly important for me to do this introduction because I'm very proud that we have persuaded Vangelis to move from Crete, being a full professor there. So I recruited Vangelis as our ERA chair for modeling and simulation for engineering applications. This complements what we were doing at that time at Castro C, which was more focused on computational sciences, and it was a great addition to the research agenda of the center. So today, Vangelis will start from where at least I stop, namely describing the atoms. That's where we stop, the systems we stop, and this is why it's complementary. Vangelis starts from the atoms and goes on to describe complex systems using simulation across scale and data-intensive computing. Please, Vangelis, the floor is yours.
So thank you very much. Thank you very much, Dina. Thank you very much for the kind invitation. So and also for the introduction. It's my great pleasure, actually, to not only to be here for the last 1.5 years, but also to give today this, let's say, general talk. So I was asked actually to give a general, let's say, talk and introduction about what we are doing, and mainly about what we call multi-scale modeling that you will see in a while. What is this? And it's a way computationally to describe, let's say, atoms up to the materials level. And for that, the important words are the simulations across scales and what we call data-intensive computing. And then what I describe here is from atoms to the design of materials. So given that I would like to give an introduction, I will start by firstly discuss a little bit these two different concepts, let's say. And for that, I will start actually from something that's even more generic, so a little bit of history. And since I'm Greek, typically we choose to start from ancient Greece and Greek history. And I will start from something which is particularly important from my perspective. So this is a concept from Plato, developed the 4th or 5th century BC. So this is the theory of forms. So according to Plato, actually, the physical world that we see is not as real or true as timeless, absolute, unchangeable ideas. This means that practically, beside the physical world that we all know, there is, okay, the mental world is just what we are thinking about the world, but beside that, there is another world, which is called the Platonic or mathematical world. So at that time, mathematics was the first, let's say, the primary tool in order to describe this world. And there is a very famous allegory now. This is the allegory of the cave. So just to remind you again, I'm sure that you've seen this before. So the main idea here from Plato, the myth or the allegory, if you want, is that there are some prisoners. Here are the prisoners. There are some people behind that they keep puppets of the real objects, subjects, and the prisoners see only the shadows of them. So they don't see actually the real world, they see only the shadows. Now, at some point, a prisoner can become free, somehow, and then he or she can go up to realize that there is another thing, which is this realm of forms or ideas of the real world. So, of course, it's an allegory, and you like it or you might not like it. Personally, I like it a lot because of its central message. So the message is that via education, pedia, we can actually, let's say, become free. So that's the main, I think, concept, the main message. And now for thousands of years, this education, let's say, or science, if you want, the main tools in order to perform, let's say, the sciences was primarily via empiricism. This is actually from the beginning of the civilization, many thousands of years. and also via the theory. Theory now, for thousands of years, again, it was primarily via mathematics and philosophy, let's say, but the last, let's say, few centuries also with the development of theoretical physics, natural sciences, and theoretical science. Okay, so these were the two main routes, let's say, in order to advance our knowledge. All these were true till about 1945. So in 1945, we have a revolution. Can you think what was the important thing happened in 1945? I should exclude people from casters. Okay, so first, of course, we know that it was the end of the Second World War. That was the good news. The same year has been, there was the atomic bomb, which is definitely not the good news. But at the same time, there was a technological revolution. And when we are talking about technological revolutions, we mean about the inventions of machines primarily. Okay, so I've read somewhere that one of the most important machines in the human history is the washing machine, because this really changed really the way that people live, at least half of the population. So this is another machine, and if you have not seen this before, then I'm sure that it's not possible to consider that this is a computer. So this is the machine of the first computer, 1945, and the name is ENIAC. So ENIAC, and you see an acronym which is not really very appealing, it's Electronic Numerical Integrator and Computer. The important thing is that this was the first machine that was able to solve a class, let's say, of numerical problems, but the key word here is programmable. So the machine was able to solve not a single problem, but many problems through reprogramming. So this has been developed at the University of Philadelphia, if I'm not wrong, Pennsylvania, if I'm not wrong. It was, of course, funded at the time by the Army. It was a continuation of what happens at the Los Alamos. And there were many people working on that. So that happened in 1945. Okay. And of course, at that time, there was a very primitive, the first machine, let's say. Now we live in 2020, and there is a famous law here, which is not a law actually, it's a semi-empirical observation, the Moore's laws, that shows the exponential increase of the computational power. Okay, so this is just an observation that says more or less that every 18 months, the available computational power doubles. Okay, and if you see now here actually it's a very interesting plot. Unfortunately, the background is not, it's black. So you see here is the calculations per second, but also per constant dollar. So this means it's for a constant price. And if you see ENIAC somewhere here, first of all, here. As you see in this plot, there were also machines before ENIAC. So ENIAC was not the first machine that was capable of solving problem, but it is considered to be the first programmable machine. Okay, that's the main difference. Actually, the first mechanical machine that was used to solve problems is assumed nowadays to be the mechanism of Antikythera, which again from the ancient, let's say, Greece, from Archimedes' area. But at that time, this was the huge thing because, as I said, we have a programmable machine. But look now the evolution. So since 1945, there are less than, or about 75 years only. It's a very small period for the human, let's say, history. Despite that, if you see here the evolution, the advancement of computational power, and again, I said per constant dollar, not the total one, but for the same amount of money, there is an increase of 16 orders of magnitude already. So there is no any other invention in human nature, in human history, sorry, that so far has saw such enormous advancement in only 70 or 75 years. So this is really a big thing. And nowadays we have from this machine, let's say, we are now in this level of machine. So this is currently the world's fastest supercomputer, Fugaku from Japan, with capability of 442 petaflops. The petaflops, or the flops in general, is just a metric that we use in order to send the computational power. Okay, so we have these things now. We have seen before this ideal world. If you like it or if you don't like it, there is this mathematics that can describe them. And now we have the machinery also here. Now, if we join this together with algorithms, and we need algorithms, why? Because in order to use the machine, we need something to program that. Okay, and we need to implement the problem and to solve the problem. And this is again a concept coming again from the ancient history. It's not the Greek history. This was well known already in the ancient Babylonian mathematicians from Babylon. The name is coming from a Persian mathematician. And as you all know, algorithm is nothing but just a recipe, in principle. A recipe in order to solve a problem. So this is the formal definition, a finite sequence of instructions to solve a class of specific problems. This is a very simple algorithm. Okay, you all know that. So here we use an algorithm in order, for example, to open or close the gate when the train arrives or the train departures. This again is a recipe, so it's an algorithm. Okay? This, of course, is very simple. There are much more complex algorithms. This is a more complicated one, but I will not try to explain to you this now. Okay, we'll need a couple of days for that. So this means just the complexity of the problem. Of course, okay, this, as I said before, is the conceptual issue that was well known. What happened also the last 70 years, we managed to develop tools in order to implement these algorithms in the machines that we've seen before. And these are the programming languages. Okay, so now we have all the concepts. So we have the machines. Of course, we've started with the mathematics and science. We had the infrastructure, the algorithms, and then the programming language. So all together, if we put all of them together, then we have an interdisciplinary here field, which is called computational science and engineering. And nowadays, this is typically we describe that as being somewhere in between, let's say, or in the overlap region between sciences, engineering, mathematics, and computing. It's a new discipline, and this is going together with what we call model. Again, it's a combination, more or less, of experiments, theory, and computation. And it refers actually to the development and application of computational model and simulations for different systems. Okay, this is, of course, part of high-performance computing, and if we couple all of them together, then we can solve physical problems, and this is our goal, actually. Now, just as a final, let's say, part of this generic discussion, this is considered to be the third pillar of discovery, because, as we have seen before, theory and experiments they were the first one, but nowadays there is another also part that has been developed the last couple of decades, which is called data exploration. Typically, we describe this as the fourth, let's say, paradigm for advancing science. And there is a very nice here pictorial evolution of science from empiricism to the theoretical branch to the computational branch, as we have seen after 1945, and then the data exploration the last couple of decades. So all these are together, and these are typically called the fourth paradigm, which concerns the data science. Okay, so these are well known, let's say, more or less, a way of describing the advancement of science the last decades. And also, I would just like to again stress out that what we describe as computational science refers to both the simulations and the data science of this. And now, all these are extremely important, of course, coupled together with mathematics and algorithms. And we can use these tools, of course, for a variety of systems, a variety of properties and disciplines, and for various disciplines. So today I will focus, of course, in what we are doing and which is related with materials. And the main goal here is, if possible, to predict the properties of materials in the atomic level, as we will see later, and also to help or to advance, let's say, the design of new materials, if possible. And then, of course, a main question, if you are not coming, if you are not, let's say, very familiar with physical sciences and engineering, is why do we need to study materials, why it's so important of materials. So again, there will be a couple of introductory here slides or things about materials. So materials are so important that not only exist, let's say, everywhere, but characterize in principle the time periods, the eras that we live. And so you all know from your history lessons that there was the Bronze Age, the Iron Age, of course there was the industrial area for several centuries, and now after 1950, together with this development of the infrastructure, we consider that we live in this Silicon Age. The Silicon Age is not characterized only by silicon from the point of view of materials, but also for more advanced materials, like, as you see here, polymers, modern composites, nanostructural materials, metamaterials, etc. So the list here is again endless. And all these are materials that have been developed after 1950. So together, let's say, with the Silicon Age. That's the primary thing. And now this actually is important nowadays because if you consider all, let's say, important societal challenges, for example, the climate change, okay, the energy, archaeological heritage, and of course the examples here have been chosen on purpose. All of them, in order to address all of them, we need to develop new materials. So without new materials, it's not possible to talk to, to consider how to save energy, for example. Okay, of course, one way is to improve processes, but we definitely need new materials with better properties, and that concerns both, let's say, the technological, from the technological point of view. The goal is to develop new advanced materials, but also, of course, from the basic science, because in order to develop these materials, we need first to understand their behavior. So this is coming the scientific path. And this is just an example of modern energy devices. So materials are really everywhere. For example, fuel cells, perovskite, MOFs, all these are considered new modern materials that could be used, for example, for solar devices, and the list is really endless here. So this is a really very broad field, and just to give you one more example, which concerns more systems that we are working on. And this is an example of polymer nanocomposites. We will see in a while what are polymers, but in general, you can consider them as nanostructure, let's say the nanocomposites as nanostructure systems, that they have really a very broad range of potential technological applications. As you see here, energy again, environmental remediation, transportation. For example, in cars are now more than 70 or 80% consist of such materials, not anymore metals. So this is very important. Also in the biomedical field, even more important in biomedicine. And all these materials now have a characteristic that belong in a category, in a family of systems that we typically call soft condensed matter. Soft condensed matter is just a family of systems that can be modified by forces which have more or less the same magnitude of thermal fluctuation. So energy is equivalent, let's say, to the thermal energy, the characteristic energy of the system. And this, again, it's a family here of different molecular systems. So you can see polymers, biological membranes, liquid crystals, etc. So as I said, the list here is really endless, and the potential applications is really enormous. So in all these cases, the main challenge, let's say, is, if possible, to predict the behavior and the properties directly from the molecular structure. So if we had, let's say, the perfect method, then we would like to, starting from the atomic or the molecular structure, predict their macroscopic behavior. And that's the main goal of what we're doing, at least, of what we are trying to do. And of course, you understand that this is a very interdisciplinary field. Actually, it's in a cross, let's say, disciplinary of several different here disciplines. So it's biology, physics, chemistry. But at the same time, if you see the people who are working on that, there is not really any. So I think it's beyond the borders that we typically use in science. So there is not really a specific field that, the scientists from a specific field that really work on these systems only. It's exactly the opposite. Actually, we need the collaboration between people from much different fields in order to address the complexity of the problem. And that's a central message of my talk today. So now I will focus, and I will start presenting a little bit the methods and some results. So for that, because we are working mostly with polymers, just to remind you what's exactly polymer. Polymers belong to a family of systems that we call macromolecules. There are many monomers or repeat units that are bound together, and they form this kind of large molecule, which is typically called macromolecule. And as you see here, this is the structure of this, which is like a random coil. As you see, it's almost spherical. Now, the actual one might not be exactly spherical. This is from a detailed model. This is a cartoon. Okay, this is a detailed model from the simulation. But it depends always on the actual, let's say, chemistry behind that, because this is also macromolecule. And this is DNA, which is definitely not a random coil. This shows, again, the complexity of the systems that we consider here. And these are beside the fact that, of course, are very important systems for various applications and for various reasons. We see here the biological systems. But at the same time, they're also a very good example of the complexity, because if you see a single molecule, let's say this, then if you see it macroscopically, you might see domains, even from a single molecule. But then if you assume that you have a microscope now, and you start focusing inside this molecule, then you will see different regions here in a level that we typically call it mesoscopic or semi-macroscopic. Then this one, that is called mesoscopic. Then we have the microscopic, where we have atoms. And then if we had even a much better, let's say, device, we would have been able to see the subatomistic, where we see electrons and nucleus. And as Dina said before, if we were even below that, then we could see quarks and all this stuff. Okay, so this is the general idea. But the characteristic exactly of the polymer is that all these different length and corresponding time scales that I saw here describe the same molecule. It's a single molecule. A single molecule that has all this very broad spectrum of characteristic length and time spatiotemporal here scales. And as you see now, if someone wants to describe them, then he or she should consider time scales from the order of 10 to the minus 15 seconds, 1 femtosecond, which are bond vibrations, up to collective, let's say, characteristic relaxation times, which can be of the order of days and years. So this is really a huge spectrum that it's not possible to be computed by any single simulation methodology. And not only that, actually, there is also another thing that characterizes the system, and this is the well-known curse of dimensionality. I'm sure that you have all heard and you are aware about it. So typically with S curse of dimensionality, we describe the complexity for phenomena when analyzing and organizing data in high-dimensional spaces. So high dimensionality and non-linear interactions. Mathematically, this means curse of dimensionality practically. And it's quite clear why this is the case for such systems. First, because macroscopic systems involve of the order of 10 to the 23 atoms. This is the Avogadro number. It's the total number of atoms or molecules within a gram of mole. So if you have 18 grams of water, this includes 10 to the 23 molecules of water. So it's impossible, of course, to simulate such numbers in a real system. And not only that, but if you assume now that this macromolecular chain, which has consists of many repeat units, and if you assume that, let's say, we have only a chain of 100, oops, sorry for that. This is not working. Okay, here. So if we have a chain of 100 repeat units of 10 different types, then we have 10 to the 100 potential combinations. This is exactly the case of dimensionality that can be made. So it's clear that such problems are practically intractable. So we cannot calculate all the systems. And this means that from the practical point of view, we need methods actually and algorithms, models, methods and algorithms across different scales that would be used depending on the specific problem. Of course, we don't need to get, let's say, to describe all the information for all the different problems. It depends actually on the specific problem and the question understanding. And this is the idea of from electrons and atoms to the macroscopic world of materials, and this is exactly the idea of what we typically call hierarchical or multi-scale computational modeling. So I'm also sure that you have seen before such qualitative, again, plots. We have here time scales and here length scales. And the idea here is to have a family of different simulation methodologies that describe a specific window in this time and length scales. And of course, the most detailed one, if we exclude the world of quarks, as we said before, is the quantum mechanical level where we have electrons and neutrons. And these are, let's say, ab initio methods or density functional theory. Okay, this is the first part of the most detailed, let's say, description. So then there are the description in the microscopic or in the atomistic level, so where we have classical interactions and all atoms in the system. Then there are this mesoscopic or coarse-grained level, as we call, and then up to the macroscopic or the continuum level. Okay. So again, since 1945, as we have seen, and the increase and the invention of the simulation methodologies, there have been many different techniques that have been developed for all these different levels of description. Okay. However, the last several decades, a main challenge is, if possible, to bring together, let's say, and to link systematically these different levels of description. And what is the reason behind that? The reason is very simply that if we want to discuss about the computer-aided, let's say, design of materials, which is like a holy grail in the community, and to be able, via computer, to synthesize new materials. Then we don't need experiments, we don't need nothing. We have only computers to do everything. But in order to achieve this, which I don't know if this will be possible ever, but in order at least to try to address this, we need definitely quantitative predictions here for specific systems. So we need to be able, if we modify a little bit the chemistry, and to predict what are the differences in the properties of the material. And that's the idea behind that. And as we say, from the point of view of the methodology point of view, it's important, if possible, to develop such systematic techniques. And now I will start a little bit with some examples, and first from the classical simulation. So I know that, I should not have put many equations, so there are not many equations here. We have this motto that if you put one equation, then you lose the half of the audience. So, but these are actually the classical equations of motion, so these are Newton. It's just, again, to remind you physics of the high school. Okay, it's not something more. So what we do here, actually, is we solve these equations, numerically, of course, for every atom in the system. And from this point, this technique, which is called molecular dynamics in the atomic level, it's quite often, or at least initially, it was claimed to be the perfect experiment. It's perfect from the point of view that we have information about the motion and the properties of every atom in the system. Okay, so from this point, it's kind of like I would say, experiment. This is not true, and the reason that it's not true is because here there is an assumption. The assumption is that we are able to get a very good U of R. U of R is the potential energy, so it's the interaction between these atoms. Okay, and it's not true because simply we know from the basic, again, let's say, or modern physics, that this is a very complex, many-body quantum mechanical problem that cannot be solved. Exactly. So whatever we do, it will be an approximation. This is an... Sorry? R are just the coordinates, let's say.
Which coordinates?
Coordinates of atoms in the system. So we have atoms here, all atoms in the system.
So it's a sum.
R is here, this. So we have the phase space, it's R, and the momentum. Position and momentum. So it's just a Hamiltonian describing the system.
Yeah, but, okay, sorry.
No problem, please. So, again, if we had the perfect, let's say, functional here to describe the system, then we would be happy. But such perfect probably cannot exist. So, in order to proceed with that, what we need is, we need a way to approximate this, and this is the mathematical model. Okay, so far we have seen the methods, we have seen a little bit of basic physics. So now we need a model, in order to approximate this unknown and, in principle, intractable functional. And this is, again, it's related with what we say here, describing the material at the atomic level. So assume that we have here atoms. Then the atoms are connected by bonds. The bonds can be described, let's say, via bond stretching, all different here functional forms. I will not go in details. The take-home message here is that there is a set of functional forms, complicated functional forms, however, still possible to use them in the numerical solution. And this is called the empirical or semi-empirical potential energy function. So this is a parameterization of the, in principle, intractable and unknown, very complex functional quantum mechanics, let's say, functional that I have described before. Okay? So this is the forms, and there are specific functions for all these interactions. Now the question, of course, is because we have here the functions, there are many model parameters. Right? So we develop the model, but we don't know what are the model parameters. The model parameters now will distinguish, actually, the different chemistry in the system. This sometimes works, sometimes it's not working. No. Anyway, yeah, so the potential now parameters, or the model parameters, let's say, are obtained either from more detailed quantum simulations or experimental data. We don't have any other source for that. Right, so again, in order to find, let's say, the model parameters here for a specific system, now it's working, okay, then we need either to use more detailed quantum simulations or experimental data. And this is the only slide about the ab initio simulations, that's the functional theory. So in the ab initio calculations, typically we either solve the system in the Schrödinger level, so each electron and proton independently, or there is a formally at least equivalent notation, and this is the density functional theory, where someone solves the density of electrons in the system. Okay, so after many assumptions, let's say there is an interaction here potential. Of course, this is much more complicated, different than the previous one, because this refers to electrons and nucleus. Okay, the point is this, the good thing is that this, of course, is independent, let's say, of the specific chemistry, because this describes the actual chemistry. It describes the electrons, so this means that we can use this method for any kind of system, based, of course, on some approximations, because again, the exact solution is not possible. Okay, if now we are able to solve this for a very small system, for very small systems, then in order to develop these model parameters that I was discussing before, we need to solve an inverse problem. So this is a very well-known mathematical procedure. The idea is that we use data from one, let's say, description, in order to develop the model parameters in another one. So here we would use data from the detailed one, which is the ab initio, in order to derive the model parameters in the classical level. So this is simply an optimization problem, and nowadays we can use many, let's say, techniques and also machine learning in order to calculate them, to solve this optimization problem. And this is the system actually in the ab initio, in the density functional theory level. As you see, there is only a single molecule, very small. So the total number of atoms here is about 100. So it's really very small, because we cannot do DFT calculations for much larger systems. However, we can do the calculations here in the single molecule level at 0 Kelvin actually, and then we have the data about the interaction potential between these entities. So what we do in the next step is simply to define an optimization problem here. We have the DFT data, we have the classical representation. The classical representation is conditioned some model parameters X, and by solving this optimization problem, for example, here we use machine learning techniques, we are able just to find the best set of model parameters that describe the entire system. And this is a typical plot in these optimization problems. You have the energy from the density functional theory and the energy from the classical interaction. As you see, the agreement is relatively good for that. So this is the way to derive, let's say, model parameters at the classical level. And that concerns actually the first part of our, let's say, hierarchical multi-scale methodology, from ab initio to the atomistic level. Now, since we have now, let's say, the atomistic models, then we can use them in order to simulate systems of the order of 1 million or so atoms, really long. We need definitely supercomputers for that. Here are different chemistries. You don't need to check here the details. And we are able to follow actually the time evolution of their atoms. And these are the videos that we can see here. So the easiest thing in this molecular dynamics or atomistic simulations is to create such videos, since we have information for each atom in the system. Okay? Now this is the pictorial, let's say, representation, but it's also important. Why? Because since we have information for each atom, then what we can do is we can label atoms. Here the atoms just have a different color. They are the same chemistry. And we have atoms, let's say, confined, polymers confined between graphene interfaces. And what we can see is we can calculate the properties as a function of distance from this solid substrate here, which is the graphene. This is very important now from the design of these materials, because it's well known that nanostructure systems exhibit heterogeneous properties. But experimentally, it's very difficult to get information at such level. And that's the advantage of atomistic simulations. And this is just a single property, which is the mass density of the systems. I get as a function of distance from the substrate, from the graphene here. And as you see, we have something, this is divided with the bulk, so it's not flat, which means that there is a region here where the density is heterogeneous. And if you see the scale here, it's only a few angstroms or nanometers. So we're really deep in the atomic scale. And again, as I said, these are important mainly for experimentalists, and the reason is that there are no experimental techniques capable actually of getting this information in such detailed level. Okay, so this is, let's say, one kind of property. Now there are many examples that I could, in principle, let's say, show you here. So there are some, let's say, characteristics about the systems that are not so important. We can also examine further questions. For example, how the properties, let's say, of a macromolecule are affected when we change the architecture. And the most characteristic here example are the star polymers. So the star polymers are like that, something like that. So we have a core, and then we have several atoms. Okay, so this is a very promising family of materials. It was possible to synthesize them only a couple of decades ago. And of course, people, the experimentalists are asking for the information because they don't know exactly what happens at the atomic level and how exactly the properties of these materials change when you change, for example, the number of atoms. And this is now the computational procedure followed here. So what we do here is we synthesize this material, synthesize in quotas in the lab, in the simulation, and from that we perform the atomistic simulations. As you see here, we have up to 1 million, let's say, atoms within the simulation domain. And from that, following the workflow, someone can calculate specific properties of them. And a very interesting observation is, for example, how the behavior of this material is changing from a random coil, which is initially, to a colloidal-like behavior by increasing the number of atoms. This is very important from the materials point of view because colloidal systems are assumed completely different than the polymers. And what we saw here is this family of star polymers can show this transition from the random, let's say, walk behavior up to the colloidal one. And this can be further extended. For example, we can use systems, or we can model systems which have two different kinds of chemistries. that they might not like each other so much. However, they are somehow connected because they are within the same star. And then you see that the structure is changing. So here is again a 2D diagram. It's a qualitative diagram. It sees how the structure and the internal, let's say, nano-segregation of these stars. This is a star. It's a very, and this again, it's directly the simulation from the simulation domain, this picture. And you see that as we increase the functionality, or as we change here the solvent, the environment, let's say, then the structure and the morphological behavior of these molecules changes. This again a very important observation of that. And then of course there can be even more. For example, this is a more recent study related with the proteins. Again here the goal is to examine proteins, and especially in this work it was the thermal stability of their structure. So as you all know, proteins form the primary structure, which is the sequence of the amino acids. Then there is the secondary structure and the ternary, the native structure here, the folding. And we were able to examine the thermal stability of them by computing different metrics as a function of temperature. Okay, all this information can be derived directly from these atomistic simulations. So these were, let's say, the good news so far. The bad news is that first, okay, all these simulations are extremely expensive. We need supercomputers, we need large systems. At the same time, we know that even with 1 million atoms, let's say, the system is still not so close to macroscopic ones. Don't forget this Avogadro. So the real system involved really much larger number of atoms. And this is again, of course, the case of dimensionality that we have seen before. So a way to overcome these difficulties is, besides, let's say, the obvious is to use parallel algorithms, advanced numerical schemes. I will not say anything about that. We use all of them that have been developed in computational and numerical analysis the last 50 years. There are many advanced techniques there. But beside that, another, let's say, way to reduce the computational cost is simply to reduce the degrees of freedom in the system. This is a well-known technique. It's called dimensionality reduction in mathematical, let's say, language. And in our language, the goal here is to derive what we call mesoscopic models. And this is via a procedure, actually, that goes from the microscopic level. So here we have all atoms. This is just the application of an operator, but it can be just a simple calculation. It's not something very, very complicated. And then from that, we develop something, we develop for the same system a model that has fewer degrees of freedom. And this is exactly the coupling between the microscopic here and the mesoscopic level. Okay, so these are called typically mesoscopic or coarse-grained models. So again, the challenge here is to derive another now interaction potential because it's in a different scale. So it's not anymore an atom scale. And again, the standard way to solve this is by trying to solve an inverse problem. It's standard, but it's not easy quite often. So again, we will define here, we define a minimization, let's say, a function, a cost function, and the goal is to minimize that. There are many techniques. I will not say anything about that. Just to mention that this is typically, we describe them as a hybrid physics-based data-driven approach. It is data-driven, first of all, because we use many data, large data sets from the atomistic simulations that we have seen before. It's also physics-based because typically we use standard physics like statistical mechanics, well-known, let's say, methodologies in order to try to address this. It's a very complex numerical problem, again, mainly because of high dimensionality of the system. Okay, so having that now, first we need to validate these mesoscopic models, and these are some probability distribution functions, actually, that are calculated in this mesoscopic level, but here we have also the information from the atomistic. So we have the target functions, let's call them, and we have also the goal, the functions that are, sorry for that. So actually, if I go just right here, what we are trying to do is to minimize this quantity. So this means these functions in the atomistic scale and in the coarse-grained level should be the same as much as possible, right? Because we minimize that. And one of these quantities is this probability distribution function that we can see here. As you see, the agreement is excellent. So for this specific system, okay, that we see here, it's specific polymer, the derivation of this mesoscopic model, let's say, works quite well. And this is, again, as I said before, this is the coupling in this level of description. Now, actually, this process can go also in a hierarchical way in several other levels. So there is no any reason why we should stay in a single level. Especially since, as I said before, the macromolecules include such a very broad spectrum of length scales. So this is what we call here hierarchical modeling. And this means that from the atomistic level we go in one kind of coarse graining, then it's a more coarse models, and this can be continued. And what we also need, and that's very important, is we need a way numerically to go backwards. So now to go not only from the more detailed to the less detailed picture, but also, if possible, to introduce, let's say, detail in the less detailed, in the mesoscopic models. The reason is very simple. Quite often, we have experimental data, or we want predictions in the atomic level. So it's very desirable, if possible, to go backwards. And there are ways to go backwards, and there are geometric techniques or machine learning, and this, again, it's a new method where we use neural networks in order to go now to solve the backward problem, which is this back map mentioned here. Okay, and from that, we are able to have this, let's say, in the atomistic level now, configurations, as we call them, of very long polymer chains, more than, as you see here, 1,000 repeat units, and molecular weight 100,000, which is relevant actually to what people are using in the processing. So this means that there is a way to have in the atomistic level configurations of very large systems, very long polymer chains here, relevant to the real processing. And if we combine all them together, then we can calculate properties that are important for the processing and for the real, let's say, engineers, for the people who design materials. And for example, for these systems, a very important property is the zero shear viscosity. It's related with the processing of them. And here you see this quantity that is actually the integral of another quantity that is called Serialization Modulus, and which can be calculated directly in the atomic level from the stresses. The sigma that you see here of Ij are just the stresses. So we have a stress, here correlation function. The stresses can be calculated directly from the configurations that we have seen before. Okay. And from that you see also that experimental data and the agreement is very good. Okay, and not only that, I think this is one of the last examples. So we can also go to non-equilibrium properties like mechanical. And so when we are, again, referring to using these materials in real technological applications, then to try to compute their mechanical properties is extremely important. And this is just a very recent methodology where we coupled here now all this level up to the continuum in order to calculate continuum properties and continuum mechanical properties. And we do that by simply starting from these configurations. Here we have the polymer and nanoparticle. This is the polymer nanocomposite system. We apply the deformation. From that we can calculate stress versus strain, and from that we can calculate mechanical properties like F modulus and etc. And not only that, but we can also, since we have data about all atoms, we can calculate something that is not possible to get experimentally. And this is the distribution of mechanical properties within the system. So when you perform an experiment, typically you calculate the average properties. But here we can calculate the distribution of local stress and strain within the system. And from that we can develop then the continuum level using standard approaches like homogenization theory. We can calculate continuum models in the system. So I will, more or less all these examples are from our activities. Let's say I would finish with another example from a recent activity. So the most, let's say, successful algorithm in the last couple of years in the field of computational biology is the AlphaFold. I'm sure that you have heard about that. So AlphaFold is using again machine learning algorithm, but also issues from the simulations, from the multi-scale simulations that we have seen before. But here just the question now is different. Here the question is to predict the structure of a protein. Now protein is again a single macromolecule. It's nothing more than that. But the goal is to predict its structure from the amino acid sequence. And this is a well-known, is the folding problem. The main issue here is, again, the case of dimensionality, because there are 20 different types of amino acids. This means that if you consider, let's say, typical protein length, which is rather short, only 300 amino acids, then the total number of these polypeptide, let's call it, chains, proteins, that can be made out of these 300 amino acids is the total number is 20 in the 300. So the power of 300, so it's practically intractable. And the way that they have addressed this problem is, again, by using a lot of experimental data for that now. The good thing for proteins is that there are many experimental data. On the contrary, for polymers there are not actually. So there are many experimental data about their structure. And then they train here a neural network based on sequence residual distances. So there are distances between residuals, the amino acids in principle here, in order to predict the final structure. Given again a data set. So this is again an optimization problem. Again we solve, let's say we try to minimize a cost function, but the cost function here is computed based on these differences between pairwise distances between amino acids. And this was very successful. Why? Because of course such models exist in the literature in computational biology for several years, and there is one competition here, the CASP, that is very popular in this field. So every year the people are trying to predict, to drive a new, let's say, better model. And as you see here, the fold, the AlphaFold, and the second version of AlphaFold overcome and they were the winners actually in this competition. Okay, that was the good thing about this, and that's why it becomes so popular. But on the other hand, there is a criticism about that, and the criticism is first that the accuracy is not high enough for a third of its predictions. So it's very high percent. Despite the fact that this is the best algorithm in computational biology, still the accuracy is not high enough for a third of these predictions. And even more important from my perspective is that this is just a statistical approach. So we get nothing about the mechanism of protein folding. So I will more or less stop here, just as a take-home message that the curse of dimensionality always will at some point. Despite this fact, the simulations together, let's say, with the physics and the data-intensive computing nowadays can be used in order to provide a part at least of what we call here fundamental understanding of the behavior. So this is the scientific part, and also to be used, I would say, as complementary tools. I don't think that we will ever be able to let's say, avoid experiments, but the point is to use them as complementary tools for the rational design of materials. And for that, we need definitely some very essential conditions. The first is to derive accurate models and algorithms in order to validate them for large data sets. So since I've started with the philosophy, I will finish with the philosophical question. So the question is it possible to develop a perfect, let's say, model or algorithm? More or less, we can use the same word here. A perfect model or algorithm that could be used for every system. So this is a philosophical question. And as a philosophical question, does not have a single answer. So I would say there are at least two answers. 1 minute more. So there are two answers or two approaches.
Yes, you
No,
know.
no, it's not this. There are not two yes or no. It's the first, I would call it engineering approach. The engineering approach starts here from a very motto which is well known. Actually, it's from a statistician, George Box, who said that all models are wrong, but some are useful. Well, I don't like so much this, because I think it's more accurate to say that all models are correct, but for the specific assumptions that they have. And then at the same time, it's true that some of them are useful for describing the real system. This is engineering, let's say, approach. And this means that, of course, since we say that there is a real system here that we are targeting on, let's say, then, of course, the absolute test is always the reality. Okay, so this means that we need experimental data. So we cannot avoid comparing our predictions with experimental data. Now, there is a second approach. I will call it mathematical approach. I could just say physicists, but since there are many physicists here, there are not so many mathematicians. So here now, we try to remind you again the theory of forms. So according to Plato, there is another world, the mathematical world. So this means that we don't care so much about if there is a real world, because we believe that model or algorithms can be even more real than the physical world. Okay, so this is a slightly different approach. I would say it's not important which one you choose. Me personally, I use both of them at different times. So, but in general, I would say, again, this is a message more to the students, of course, and not to the students of Casper, to the rest, that it's a fantastic period to be involved. And the reason is very simply that simulations and data-intensive computing and infrastructure are still in their infancy, only 7 years. At the same time, we are now developing, we're in the process of having new machines in the exascale capacity. These are at least 3 orders of magnitude of more than what we have now, and this will be available in the next few years, 2 or 3 years. So this is really a huge increase.
In a year.
Huh? In a year, yeah, but now with the problems of the logistics, it might take more. And at the same time, something which typically we don't focus so much, but from my perspective is very important, that we are able to explore and share large data sets. And this capability now is increasing again exponentially. And all the effects that increase exponentially, we will see definitely huge, let's say, advancements in the next few years. And for that, of course, from the societal point of view, it would be possible to address very, very important problems. Okay, so I will stop here, but this is probably the most important slide. So I would like to acknowledge a fantastic group of excellent people, students, postdocs, collaborators, and all the CIMEA, also students from the Fourth and the University of Crete, also, but there is a worldwide, let's say, collaboration network. Here are only the active collaborations with specific projects. Of course, I would like to thank the funding and even more the Castor C and the Institute for supporting us for this 1.5, almost 2 years now. It's a fantastic period, and I'm really grateful for that. So thank you very much for your attention.
Thank you very much, Vangeli. So the floor is open for questions from non-Castor C people.
Thank you very much, Vangeli, for offering something that is very complicated and trying to say that this is very simple, and but also explaining many principles to the extent possible in a simple way, thinking very macroscopically, and keeping in mind sustainability challenges right now, things that are related to the so-called circular economy, which could have to do with recycling of plastics, with valorizing waste to make new fuels or raw materials. Does this aspect pose additional challenges to your models, or if your modeling can understand the basic physics of polymers, for example, or other materials, you believe that this is just another application that can easily be tackled?
So thank you very much. Of course, this is a very important point. So again, I think it's a little bit a matter of perspective. So if you see, sorry, this is not working. Back. No, suddenly back. Sorry. No, the back button is not working. So I would like just to say that in principle, let's say from the mathematical point of view, the methodology is there, is the same. But from the practical point of view, the differences are really huge. So when you try to go, let's say, to the atomistic level, and you try to describe this U, okay, this is very simplistic of the picture here. This here now, potential energy functions would depend strongly on the actual chemistry, on the underlying chemistry. So for example, for the cyclic economy that you mentioned, we have the standard, let's say, polymers that are not biodegradable, and then we have biodegradable polymers. Quite often the chemistry is much different. So this means that in order to develop, let's say, to study them, then we need to be able to find such semi-empirical, let's call them, functions to describe accurately these biodegradable polymers. And exactly because this is a new field, and so far there were not many data for such polymers, currently there are not many accurate ways to model it. But this is exactly because there are many people working in this area, there are more and more available experimental data. It is for sure that within the next, let's say, few years or decade, we will have more works on this field. So this field, the biodegradable, together with the polymers for energy applications, they are by far the two most, let's say, active research areas from the point of view of application.
More questions for everybody now? Please.
Hello. For this kind of simulation, what kind of criteria do you use to finish the simulation and say that this is conventionality, what we get?
Okay, this is again a very important question. So this depends entirely on the problem under study. Okay, so typically, because I try to not include many equations, so what we are trying to do here is important. Okay. Let me just give you an example. So here we perform the simulations, and exactly as you say, the simulations can be very long. So let's say that we try to calculate one property like the density here. Okay? So the standard thing that someone could do is to examine the time scale above which this profile here, which average, of course, this is the average density, does not change time.
Okay, so it's average quantity.
Average quantity.
It's not time dependent.
There are also time dependent, of course. There are many time dependent quantities, so that's the other thing. And the time dependent quantity, because sorry, now we were a bit below. This is a time dependent quantity because it's in here. Because this, if you see here, we have time. So this is an autocorrelation function in time. So the other criterion is to find where this integral converges. Because here you see the integral here goes from 0 to infinity. Of course, we cannot go to infinity. We should stop somewhere. But fortunately, we can see that this, we can find the time scale in which this integral constrains, but this integral refers to the stress here autocorrelation function. These are just two examples. Please.
Somewhat related to this question. The thermodynamics of these systems is a nightmare, as you know. Classical thermodynamics do not apply, non-equilibrium, actually. I know it's a very active field in statistical mechanics and thermodynamics. What kind of thermodynamics do you use in your simulation for thermalization of the system?
Good, that's also a great question, but as I said, I try to describe anything without the question, so it's not possible. The back.
But I don't want to see the equations of this because I know it's several.
No, the point is if I go a little bit back here in the classical equation. So of course this is valid in the microcanonical ensemble where the temperature is only the energy is constant and this is Hamiltonian. There are extensions of this. So there are extended, let's say, versions, extended Hamiltonians. That's one way, which are rigorously obtained. Yeah? So we have the bath here as an extended Hamiltonian. That's the one way to implement thermalization, to get constant, let's say, temperature. The second way to have them is to use stochastic operations, like the Lanzevin. So in the Lanzevin description, we have this classical, let's say, deterministic part, and on top of that we have friction and random noise. This was related with the physics.
But that assumes equilibrium.
Here we have equilibrium in most of the cases. So now if you are in a non-equilibrium, this you are absolutely right, it's much more complicated.
It's most of the case,
it depends. So in these systems are typically in equilibrium, so for most of these problems. Of course, in the for the mechanical property, the systems are out of equilibrium. So there it's again a matter of, if we are close to equilibrium, let's say that you are linearly reversible thermodynamics, then these methodologies or these techniques can be applied. If you are far beyond equilibrium, then there we don't know anything but to answer. Because we cannot even define the concept of temperature. So we have definitely other issues.
More questions?
Why do you have this bifurcation? These
Well,
people,
I
do they see the different roles?
they can ask more complicated questions. Parents.
Please, loud. Okay, yeah, right. That's a very good question. Excellent. I was looking for this question.
Could you repeat it?
Yeah, we just repeat it here. So when we go, let's say, from this level here, from the level of atomistic to the mesoscopic, okay, we define, let's say, here an operator, which can be, for example, the center of mass, a linear thing, so it's not something complicated. But then when we solve it, we define a cost function. And if you understand, well, the question is what kind of G is within this function, right? So typically, again, because as you know even better than me, as a physicist, everything in nature is energy, right? Energy and derivative of energy, which are forces. So practically here we use energies and forces. That's the most standard one. But we can use also structural quantities like this,
And the reason is why? Because these are actually derived via Boltzmann distribution, so these follow, let's say, e to the minus beta u. So if you match the probability distribution function of structure, you match more or less the underlying free energy in the system. All these are in the free energy level, because we have actual temperature. Thanks.
More questions?
I don't know if I'm a class or C person or not.
I said
So,
Costas.
You're in both. You're in both categories.
Both. Okay. Of course, it's an old problem, but going to effective degrees of freedom could be a big challenge in going to changing length scales. It's known that you miss important phenomena. You never discover superconductivity by studying the atomic forces. If the experiment didn't exist before, nobody would have thought of the effective degrees of freedom described superconductivity. So is there a danger in these complex materials that you'll just miss the nice things, that the effective degrees of freedom that you are constructing will be missed?
Yeah, definitely. Again, this is
how is that?
Again, this is a very important thing. So actually, one part that I didn't have time to discuss at all concerns the uncertainty quantification when you do this passage from. Sorry. Okay, I hope now it's fine. So there is an uncertainty, let's say, quantification when you go from one level to the other. So this is a very open area, definitely. So practically, that's why I mentioned this backwards problem here. So practically, exactly in order to overcome these problems, because as you said, there is no free lunch, so you do something. There are these numerical schemes, numerical algorithms, which in this case are, which are machine learning type of algorithms, which introduce atomic detail in these mesoscopic structures. So this is an inverse problem, and from the less we introduce more. So this is an ill-posed mathematical problem, and the only way to address it is via algorithms. And nowadays there are geometrical, let's say, algorithms or machine learning methods that introduce atomistic detail in this mesoscopic level. So it's an indirect way to overcome this. But of course, it's always, depends. The point is all these techniques can be described, let's say, in a nice framework, but all of them are practical problem specific. Okay, so this means that we need to see for specific problems. Just as an add-up here, let's say, comment related also what Feld was asked before. If we have, for example, a polymer that is practically used in energy, there quite often we are interested about charge transport. Charge transport is a quantum mechanical problem, by definition. So there are such issues, definitely, how to deal with it.
More questions? No? Good. Yes. What if somebody was going to ask you to define or give the silver bullet? Say, this field predicted this useful construct, this material that was not possible without this heavy machinery. What would you say?
There are many actually.
One,
I would say the most well-known, the most, let's say, mature as a field is the drug design. Drug design. So in drug design, these techniques, and the reason is very simple, the drugs are small molecules. They're not like this. They're not very large macromolecules. So in this, let's say, sector, the simulations are used quite a lot in the last couple of decades as a normal daily tool in the R&D departments. So there they know and they use it every day. And together, of course, nowadays with the data methods, they are even more.
Yeah, but this is to be the devil's advocate. You said it already, because what says that is that they are very simple molecules.
Clear. Exactly.
If you go to complex,
this is.
What would be the answer?
There are some, okay, it's true that nowadays there are more and more, these techniques are used as a complementary, let's say, tools together with experiments. also in polymer designs, for example. Nanocomposites is a big thing now because they don't have many data about them. For example, there are, again, there are, let's say, molecules that they have been synthesized based on the prediction of some simulations as well. So typically, as also in drug design, the idea is not to try via simulation to find the perfect system, but more important is to try from a potential list of many potential, let's say, candidates to do a first screening. Now that's the way that's used also in drug design. Nobody expects to find the perfect, let's say, drug from this. But it's the first screening which is extremely important for them because these are extremely expensive experiments. Or to synthesize these things and to do the experiments are extremely... nowadays with the simulations, all these are more or less free, except, of course, the cost of infrastructure. The simulation. But it gives out.
Right. Any more questions? May I ask one more?
Of course.
I mean, you mentioned about this protein 40 and the 20 to the 300 combinations, but of course a lot of these combinations can be eliminated, right? So are they techniques to reduce the problem? Because a lot of it will be not physical or suppressed or...
Yeah, there are many techniques to try to do that. The point is this, the AlphaFold and let's say all these methods are primarily based on statistical technique, right? So they need data. That's the key here. And the data, in most of the cases here, are coming from the experiments. There are experimental data. I think from the order of about a few million proteins, which is not, of course, comparable to what we see here, but again, it's a lot of data. The thing is that, that's why I think it's very successful now, it's very popular, this method, is that because they are considered the first step, and it's for sure, as the time passes, there will be more and more available data. So the idea is in a few years, the accuracy will be increased. But of course, as I said, this will not say something about the mechanism. So that's why it's more like, applied statistics, and it's not really about the mechanism for the protein folding. So again, from my perspective, these are more complementary techniques. So let's say that HPC simulations will go together with this data methods, in order to address such complex problems.
Okay, so let's wait for quantum computers.
Quantum computers, there is another, yeah, definitely. That could be even more, yeah.
Okay, well, thanks very much for the great talk.
Thank you very much.